Welcome to the session. Today we are going to discuss dual of a planar graph and graph coloring. See what is meant by a dual of a, how to construct a dual of a planar graph. Consider a connected graph G, and any planar graph if I am going to consider, then definitely it will produce us some reasons. Let those reasons are R1, R2, R3 and so on be the reasons. Then whatever the reasons will be there, any planar graph, then we are considering all the reasons, whatever the planar graph is having, all the reasons were denoted as the vertices. As the vertices. Suppose there are n reasons are there, then we can get n vertices. If there are 5 reasons are there, we can get 5 vertices in the dual of its planar graph. So that is the main first concept. That means whatever the number of reasons will be there in the planar graph, its dual, while we are going to construct a dual, then the number of reasons is nothing but the number of vertices in its dual. Now, number of vertices is over. Now, number of edges we are going to consider. Now, let us see, if 2 reasons are Ri and Rj, if they are adjacents, say adjacent means they will have one common edge, Ek. Then we are going to draw one line, Ek star, joining the points Vi star and Vj star. Vi star represents reason Ri and Vj star represents reason Rj or J. So which is going to be intersect the common edge exactly once. So now let us go for this is how to construct the edges. Now if there are more than one edge is common, if there are more than one edge is common to Ri and Rj, draw one line Ep star between the points Vi and Vj star for the common edge Ep, intersecting Ep exactly once. So whenever if I am going to get like this, see here there is one more edge is common between 2 reasons, draw one line Ep star between Vi star to Vj star for each common edge. That means if there are number of edges are more, then we have to construct the common edges. Whatever the common edges are there, for each and every common edge, we have to construct one edge. And another one is, for an edge Ei lying entirely one reason, then say Ri, draw one loop. That means, suppose if I am going to have, let us say, I am going to get here, one edge will be there, which is Ei is an edge, and entirely lie in one reason. Let us say Ri is the reason. Then we have to construct. The reason is I am taking like this. Then we are going to construct one edge which is passing exactly once to the edge, and we are going to connect once again to the vertex. So like this we are going to get. So these are the different ways. That means any pendant vertex is there. While we are going to construct a pendant vertex, then automatically we are going to get a loop corresponding to Ei, pendant edge. So these are the 4 basic principles. Now based on these 4 basic principles, now we are going to construct a dual of a planar graphs. Now let us go for, we are going to discuss one graph. Let us say this is the graph. And now let us, I am going to consider this is the graph. So now here what are the edges? Let us say vertices are V1 and V2 and V3 and V4 and V5 are the vertices. And the corresponding edges are, let us say, E1, E2, E3, E4 and E5, E6 are the edges. So this is a planar graph because it will produce the regions because there is no edge is intersecting other than the vertex. So it gives some edges. Let us say what are the edges, what are the reasons? Some reasons. R1 is one reason, R2 is another reason, and R3 is another reason. Now for this, we are going to construct one dual graph for this. So for that, we are going to say this. We are going to write once again the same graph we are going to construct. And now, see here. Now, this is one reason. Let us say reason R1 is considered as vertex V1, and reason R2 we are going to consider as vertex V2, and reason R3 we are going to construct as vertex V3. V3 dash. So let us say V1 dash, V2 dash and V3 dash are the three reasons. Now are the three vertices in its dual. Now let us say for this I am going to construct one edge corresponding to E1. So E1 I am going to construct, then this is the edge. So this edge is corresponding to E1. We are taking it as E1 star. And while this vertex is, I am going to take it as V1 star. And this vertex is V2 star we have to consider. And this vertex is V3 star. Now corresponding E1 edge we are going to construct. E1 star is the edge of its dual. And next another one is for E2. We are going to construct one more edge. Let us say it is known as E2 star. And now this is a common edge is there, E3. So for that we are going to construct one more edge. Let us say this is E3 star. And next we are going to consider E5 and E6. So I am going to construct another edge, so which is passing through E5 and connecting to the vertex V3. So here I am going to say it as a E5 star. And another one is E6. E6 we are going to get, this is E6 and the corresponding edge is E6 star. We are connecting like this, E6 star. And here that means for each and every edge there is a corresponding edge will be there in its dual. And now if I am going to consider a dual, let us say I am going to consider a pendant vertex, let us say E4, then we have to take the corresponding edges, nothing but we are going to get the corresponding edges like this. So this is a E4 star. So this is the edge, whatever the edge that we are going to get. And if I am going to remove the main graph, then whatever the reduced one, if I am going to get. So this is the dual of original graph, let us say G. And dual of G is, let us say, we are going to consider G dash. So this is a way that we are going to construct the dual of the given graph. And now let us go, I am going to consider another graph. Let us say we are going to take another graph. We are saying that this is another planar graph. So this is the planar graph. And now it will give the reasons 1, 2, 3, 4, 5 reasons, because inside reasons are 4 and outside the reason is 5. Outside the reason is another reason is 5. And now we are going to construct the corresponding vertices. This is for R1, this is for R2, and this is for R3, and this is for R4, and this is for reason 5, R5. And the corresponding are nothing but V1 star, V2 star, V3 star, and so on. V5 star. So here let us say if I am taking corresponding to this edge, I am going to construct another edge. Let us say E1 star. This is E1 edge. For that E1 star we are waiting. And next for this, let us say this is E1 and this is E2. For this I am going to get another edge. Let us say this is E2 star. Then we have to consider one more. So this is E3 star. Let us say E3 star. Then for this edge we are going to construct another one is E4 star. Then for this edge we are going to construct another one is E5 star. And next for this edge we are going to consider another edge. Let us say this is E6 star. This is the another. That means whatever the number of edges will be there, the same number of edges will be there in its dual, and whatever the number of regions will be there, the number of vertices will have in its dual. Suppose if I am going to consider another graph, let us say I am going to consider a complete graph, let us say with 4 vertices. Just I am going to consider this is this, and now let us if regions are, this is one region and this is another region and this is another region and this is another region. So now we are going to connect this. So just I am going to connect. I am going to connect like this. So I am going to get this is corresponding to this edge, and corresponding to this edge I am going to connect like this, and corresponding to this edge I am going to connect like this, and corresponding to this edge I am going to connect this, corresponding to this edge I am going to connect this, and corresponding to this edge we are going to connect this. So the dotted lines are nothing but the dual of the original graph. And let us say we are going to consider another graph. Let us say the graph will be, we are taking like this is the graph. Now see here, this is another planar graph. Now the regions 1, 2, 3, 4 and 5 is outside the region. Let us say the regions are, we are taking it as vertices. And next outside we are going to consider like this. And now see, for this edge we are going to connect like this, and for this edge we are going to connect like this, and for this edge we are going to connect like this, and for this edge we are going to connect like this. Internal edges are over. There are 4 edges are there. So corresponding its dual, we are having 4 edges. Now external 4 edges we are going to connect like this. So this is one more. For this edge and for this edge we are going to take like this, and for this edge we are going to connect like this. For this edge we are going to take like this. So it is nothing but just we are going to call it as, for this edge E1 star, and for this edge E2 star, for this edge E3 star, and for this edge E4 star, and E5 star, and E6 star, and E7 star, and E8 star. So there are 8 edges will be there. So subsequently we can get 8 edges in its dual. So one more concept is there. Any dual of a dual is nothing but the original graph. Suppose if I am considering a dual of the above of the graph G2, let us say this is Z1 and this is Z3. G2 dual is G2 dash. What we are having? We are having, this is like this. I am going to take, and now for this I am going to connect like this, and for this is there, and for this one more is there. So we are going to get the dual is like this. And now if I am going to connect once again the dual regions, it will produce some regions. Once again we have to connect all the regions. So then we are going to get the original graph. For that. So any dual of the dual, we are going to get the original graph. Now, some of the important results which we observe from this planar dual of a planar graph. There is a one-to-one correspondence between the regions of G and vertices of G dash. So number of regions will be there, n number of regions, and number of vertices in its dual is also n. There is a one-to-one correspondence between the edges of G and G star, of G and G star. So there is a one-to-one correspondence between the number of edges, how many number of edges are there in G, and the G star is also having the same number of edges. Now any pendant edge will be there. Any pendant edge will be there. It will give loop. It will give a loop. Any loop will be there. Any loop will be there. Then we are going to get a pendant edge. Pendant edge. Suppose if I am going to consider any loop if I am going to consider, let us say if I am going to take a graph is like this. A graph is like this. So the corresponding is 1 we are going to get, and this is another reason, and this is another reason. So for this we are going to connect, for this we are going to connect, for this we are going to connect, and for this we are going to take, we are going to connect only the pendant edge, okay. That means the edge which we are going to create for the given edge, it crosses only once of the given edge. So any loop will be there, it will give a pendant edge in G dash. And edges that are in G yields parallel edges in G, and parallel edges are in G leads and in series are in G star. So edges we are going to consider, there are, see here this is one edge and this is one edge. So this will become parallel edges in G star, and parallel edges will be there. Then it will yield edges in series in G star. Number of edges in which form a boundary of the region Ri, then in G equal to the degree of the corresponding vertex in Va. So in G star. So here number of edges which are, suppose the boundary, what is the reason for this? What is the degree of this reason is number of edges which are going to be bounded for this. So the equal to the degree of the corresponding vertex. So from this we are going to get any number. Let us say what is the vertex of this degree is, then it is crossing once, and this is crossing once, and this is crossing once. So corresponding to this reason, if you are going to construct any one edge, any one vertex, then the vertex degree is nothing but which is equal to the number of the degree of that corresponding reason. So here the degree of the reason is 3. Then from this, if you are going to get any vertex, then the degree of the vertex is also same, and it is vice versa. And like G and G star are connected. G is a connected planar graph. Obviously, G star is a connected planar graph. If G is a connected planar graph with n vertices and m edges and r regions, then its dual is also considering n star vertices, m star edges, and r star regions. Then we are going to consider these are all equal to each other. So n star is equals to number of vertices must be equal to number of edges. Number of edges in dual is equals to number of edges in the original graph, planar graph, and the number of regions in the dual is equals to number of vertices in the original graph. So this is the concept, some of the important results which we come across while constructing a dual of a planar graph. Now, the next concept is graph coloring. What is a graph coloring? So graph coloring is also called as a vertex coloring. See, graph coloring is nothing but a properly colored graph. Then any graph which is properly colored, then we can say that this is a coloring of a graph or nothing but a properly colored graph. That means what is a properly colored graph means it ensures that there exists no edge in the graph whose end vertices are colored with the same color. Such a graph is called properly colored graph. See here, we are considering one graph. Let us say this is having the vertex V1, V2 and V3 and V4 and V5. Let us say the vertices are like this. Now, some color is going to be assigned for V1 and it is having two adjacent vertices, V2 and V5. Those two adjacent vertices will not have same color. Then any adjacent vertices will not have same color. Then that is known as a properly colored graph. Now here some color will be there. Adjacent vertices will have different colors. And next, this is having one vertex adjacency and this is V4 is adjacent vertex. Of course, these two are adjacent vertices. Then in whatever the manner that you are going to consider, V3 and V4 are adjacent. So V3 and V4 are different colors. V2 and V3 are adjacent vertices. They are in different colors. V4 and V5 are adjacent vertices. They are different colors. So this graph is a properly colored graph. That means no two adjacent vertices are colored with the same color. Therefore, it is a properly colored graph. So, in any manner that you are going to consider, the adjacency vertices will not have the same color. Such a graph is nothing but a properly colored graph. And here, while we are making the graph is properly colored, see any number of colors that we are going to use. To make the graph is a properly colored graph. Now, to meet the minimum number of colors that we are going to use, and with that you made the graph is properly colored, such a minimum number is known as a chromatic number. So here, the graph is colored. See how many colors that I am going to use here? So 5 colors I used. 5 colors I used to make the graph is properly colored. Is it 5 colors are required to make the graph is properly colored? I can use only 3 colors. Let us say I am going to take it as this is alpha 1 color and which is adjacent to then V2 and V4, V2 and V5. So I am going to assign V2 and V5 are different. So I am going to assign different means they are not adjacent. So V2 and V5 I am going to assign beta color. And the remaining vertices, so here they are adjacent. I cannot assign the same color. So I can assign alpha color. And here I am going to assign beta gamma color also. I am going to assign. So here I cannot assign alpha color because these the two are adjacency. So I cannot assign alpha color. I cannot assign beta color. And so I can assign some other different color. So what with this, with the help of 4 colors, what is alpha, beta and gamma. With the help of 4 colors, I made the graph is properly colored. Here I used 5 colors. So here I am going to use minimum number of colors to make the graph is properly colored. That minimum number is known as a chromatic number. So here chromatic number is nothing but the minimum number of colors that we are going to use to make the graph is properly colored. Then it is known as a chromatic number. Now there are some examples will be there and we are going to find out what is the chromatic number of the graphs. Okay, see here earlier whatever we discussed. So the same thing. See here. See what is this? Here we are taking it as alpha, beta and 4 colors. And here let us say the chromatic number same. What is this? This is 1 color. This is 2nd color. This is 3rd color. See, observe this. See here we are made it as alpha, and the next another one is, see here, this is 2 and the same color, and we are going to assign, see here, alpha, beta, gamma. Sorry, this is only 3 colored. I am going to use only 3 colors here. Here it is 5 colors. So we can say this is, here it's not 4 colors used, only gamma up to gamma, alpha, beta, gamma. So the chromatic number of this graph is 3. So 3 colors that we used to make the graph is properly colored. The same thing we are explaining here. The same thing. So in this, I'm going to use only 3 colors to make the same graph is properly colored. So the chromatic number of the graph is only 3. Instead of, we can make it as with 4 colors also properly colored, with 5 colors also properly colored, with the 6 colors also we can make the graph is properly colored. But the minimum number of colors that we are going to use to make the graph is properly colored, such number is known as a chromatic number. See here, we are going to consider some of the complete graphs. So this is a complete graph with 4 vertices. So complete graph with 4 vertices, the chromatic number is 4. Complete graph with 5 vertices, the chromatic number is 5. So in general, complete graph with n number of vertices is nothing but a chromatic number is n. So here, because it is nothing but a complete graph with 4 vertices means each and every vertex degree is 3. Each and every vertex degree is 3. So there are 3 adjacent vertices will have. Subsequently, there are 3 adjacent vertices will have, and all these 3 adjacent vertices are also mutually, they are adjacent to each other. So for that reason, I am going to assign 3 different colors for the adjacent vertices, and one more color I am going to assign where we started. So that is nothing but the chromatic number is nothing but 4. And similarly, any complete graph, if you are going to consider 5 complete chromatic number, the complete graph with 5 vertices, Kuratowski's first graph. So here, each and every vertex degree is 4. That means 4 vertices are adjacent to it. So all 4 vertices will have the different colors. Of course, the given vertex is also with the other color. So subsequently, we are going to get the chromatic number is 5. Now, if I am going to consider any cycles will be there in any graph, then what is the chromatic number? So here I am having a cycle here, and here the chromatic number is 3, and here I am going to get a cycle, and next the chromatic number is 2, because here I can assign 1 color here and opposite 2 colors. So it is nothing but a 2 colors. With the help of 2 colors we can made a graph is properly colored. Of course, this is discussed already, and the chromatic number of this is just we are going to assign. So different with the help of 2 colors only. So the chromatic number is 2. Suppose if I am going to consider a bipartite graph, So any bipartite graph if I am going to consider, because this is not having any edges internally, this is one bipartite. Okay, this is another bipartite. There should not be any edges between vertices of V1, and there should not be any edges between the vertices of V2. Subsequently, all the vertices which are in V1 and which are in V2, they are not adjacent to each other. So, whatever the vertices will have in V1, we can assign 1 color, and whatever the vertices will have in V2, we can assign another color. So the graph is, any bipartite graph is having a 2 chromatic number. Okay. Then, suppose if I am going to consider any trees, and here trees also the chromatic number is only 2. Now, this is some brief concepts just to find out the chromatic number of that. Then some examples that we have to consider. Let us say a bipartite graph K23. That means 2 vertices will be there in V1 and 3 vertices will be there in V2. This is one bipartite and this is another bipartite. Now, so here the thing is how many proper coloring of the given graph with A comma B are colored with the same color. So here what I am saying that, let us say this is A and this is B. And next this is F, G, H, let us say. Now, how many, the question is, there are a lambda number of colors will be there. There are lambda number of colors are available to make this bipartite graph is properly colored. Let us say, I am just taking K23, a complete bipartite graph, which are having V1 is 2 vertices and V2 is 3 vertices. Now, see how many ways, how many properly coloring of the graph which is having A and B will have the same colors. A and B will have the same color. So I can assign any one of the color to A as well as B. So there are lambda colors will be there. Subsequently, I can assign lambda ways. I can assign lambda ways in for coloring A and B. There is no constraint. A and B will have the same color. A and B will have the same color. So I can assign A in lambda ways colorings are given, and B also I am going to assign lambda ways. Same color. Then F is going to be assigned whatever the color that I am going to use for A and B, that color should not be used for F, G, H. Because A and F are adjacent. A and G are adjacent. A and H are adjacent. So F, how many ways that I am going to coloring? So it is nothing but lambda minus 1 ways. So whatever the color that I used in A, that color is not going to be used for F. And similarly, G is also the same way, lambda minus 1 ways that we are going to assign the colors to G. And H is also I am going to assign lambda minus 1 ways. Lambda minus 1. So the total number of ways I can assign A and B as the lambda ways. And next F, G, H in how many ways? Lambda minus 1 ways. And F and G is lambda minus 1 ways. And this is lambda minus 1 ways. So I can get lambda minus 1 whole cube. This is for the first one. That means in how many ways the graph have vertices A and B will have the same color. Suppose A and B will have the different colors, then A can assign in lambda ways and B can assign in lambda minus 1 ways, and F can be assigned. These two colors are not going to be assigned to that, so lambda minus 2 ways, and G can be assigned in lambda minus 2 ways, and H can be assigned in lambda minus 2 ways. So the total number of ways that we are going to assign the number of colors are lambda into lambda minus 1 into lambda minus 2 into lambda minus 2, lambda minus 2, lambda minus 2. So we are going to get, this is the total number of ways that we are going to assign, different colors for A and B. And what is the chromatic number? These many ways that we are going to assign if A and B will have different colors. So what is the chromatic number of this graph is? Suppose if I am taking only see, this is the chromatic number and lambda colors, that whatever the colors that we are going to use, and that based on that we are going to get this. And now same thing. Now here another concept. If delta of G is the maximum degree of all vertices of G, then prove that this is the chromatic number of the graph. We are going to represent it as chi of G, which is equals to 1 plus a delta of G. Delta of G is nothing but a maximum degrees of all vertices of G. So now let us, we are going to prove this by using mathematical induction. Then suppose if it is, let us consider n is equals to 2 vertices, and then we are going to get then I am going to connect this with an edge. So what is the maximum degree of this is V1 and V2. What is the maximum degree of the of the graph is? Then we are going to get it is equals to 2. It is equals to 2. So sorry, this is maximum degree is 1 only. 1 only. Then what is the chromatic number of this graph is? If I am assigning alpha color to this, then definitely I am going to assign beta color to this. So what is the chromatic number of this is chi of G is 2. That is nothing but 1 plus 1, which is equals to 2. Which is equals to 2. So we can easily identify whenever n is equals to 2, then we can get the inequality is 2. Suppose now we are going to assume by induction method, then we are going to, let us consider, assume that the inequality is true for n is equals to k. So it is true for n is equals to k number of vertices, then this is going to be true. Then we are going to prove the inequality is true for n is equals to k plus 1. N is equals to k plus 1. So now we are going to consider a graph G dash, which is having k plus 1 vertices. Which is having k plus 1 vertices. A graph which is having a k plus 1 vertices. If I am going to remove any one vertex from this graph, and the reduced subgraph is H. I am going to consider G dash is a graph which is having k plus 1 vertices. K plus 1 vertices. If I am going to remove one vertex, then the reduced graph is H, and of course it is having k number of vertices. Then by assumption it is true for k number of vertices, then I am going to write it as chi of H is less than or equals to 1 plus delta of H. 1 plus delta of H. Because this inequality is true for n is equals to k number of vertices. N is equals to k number of vertices. So we are going to, the inequality is true for n is equals to k. K is nothing but, we are having number of vertices k are nothing but just that is nothing but H. H. So obviously, what is delta of H? What is the maximum degree? Maximum degree of H is obviously less than or equal to maximum degree of G dash. So I am going to write it as chi of H is less than, delta of H is less than or equals to delta of G dash. And now we are going to have, this is equation 1 and this is equation 2. Now I am going to consider a small graph, let us say on a particular graph, let us say, then I am just considering a graph is like this. Suppose this is the original graph G, let us say, and here there are vertices V1, V2, V3, V4 and V. This is Z. I am going to remove vertex V from G. Then what I am having? So I am going to get a subgraph V2 and this is V3 and this is V4 and I am going to connect and I am going to take this. So here V is removed means all adjacent edges, whatever the adjacent edges which are passing through the vertex is also removed. So let us consider this as H. Now the thing is, whatever the color, that means I am going to take it as G dash. Let us say this is having K plus 1 vertices, K plus 1 vertices, and this is having K number of vertices. And this inequality is true for this. And now the thing is, whatever the colors that I am going to use to make the graph is G dash, to make the graph G dash is properly colored, the same number of, that means the chromatic number of G dash will be the chromatic number of H, That means I can say that whatever the colors, the minimum number of colors that we can use to make the graph G dash is properly colored, the same number of colors that we are going to use to make H is also properly colored. See here, let us say for this example, alpha is one color I am assigning, beta, and this is adjacent, gamma I am taking, and this is adjacent delta, and I am going to take alpha. So this is I am going to use 4 colors here. With the 4 colors, I can make the subgraph is also properly colored. So for that, in such a case, we are going to take it as a gamma chi of G dash is equals to chi of H. So now let us say this is equation 2. Now I am just combining equation 1 and equation 2. So what I am going to get? Chi of G dash is equals to chi of H, which is less than or equals to 1 plus, and here delta H is less than or equal to delta G dash. So this I am going to replace here. So what I am going to get? Delta of G dash. Equation by equation 2. This is equation 3. This is equation 3. So equation 1 if I am going to substitute, equation 2 if I am going to substitute in equation 1, then I am going to get chi of H is less than or equal to 1 plus delta of G dash. Let us say this is equation 3, and of course I am going to consider this as equation 4. Then from equation 3 and 4, then I am going to write chi of G dash is less than or equals to 1 plus delta of G dash. So this is another one. Now the another concept is prove that any connected planar simple graph is 6 colorable. So here, for that, any connected planar graph, if I am going to consider, 6 colors are enough to make the graph is properly colored. So only 6 colors are enough. Any connected simple planar graph if I am going to consider. So here also, okay, by using induction method, then I am going to consider n is equals to 1, n is equals to 2, n is equals to 3, because I am having 6 colors. So up to n is equal to 6, and 6 vertices, it is trivially satisfied. So n is equal to 1, I can assign one color, n is equal to 2, I can assign another color, n is equal to 3, I can assign like that. So the base step is going to be satisfied, and we are going to consider the assumpted step is, let us say the theorem is true for n is equals to k vertices. N is equals to k number of vertices. And now we are going to prove that the theorem is true for n is equals to k plus 1 vertices. The theorem is true for n is equals to k plus 1 vertices. Now let us, I am just taking G dash is the graph which is having k plus 1 vertices. G dash is a graph which is having k plus 1 vertices. So whenever G dash is having k plus 1 vertices, from this I am going to remove one vertex, then I am going to get a subgraph, let us say H, which is having k vertices. So what is that? G dash minus V. G dash minus V is equal to H. So G dash V minus V, which is having, let us say I am just taking straight away the same G dash minus V, which is having K, k vertices. And the theorem is true. The theorem is true for assumpted value is 6 colorable for k number of vertices. K number of vertices. Now, whatever the deleted, whatever the removed vertex, if I am going to consider, removed vertex V, see there is one problem will be there in the last session we discussed. Show that every connected simple planar graph with less than 12 vertices must have, see this is not required, see anything, see this is not correct, see any planar graph if you are going to consider, then it is having at most 5 vertices are adjacent. At most 5 vertices are adjacent. So that means if I am going to remove this V and G minus V is properly colored because it is having k number of vertices, and the removed vertex V, which is at most 5 adjacent vertices. At most 5 adjacent vertices. So for all 5 vertices, if I am going to assign 5 different colors, and for V, if I am going to assign another color, then the graph is also 6 colorable. So the theorem is true for the graph which is having k plus 1 vertices. So that the theorem is true for any number of vertices. So whenever if it is just by using mathematical induction, we are going to prove this. So the base values are obvious because up to n is equal to 6, and the theorem is true for, this is the assumpted step, n is equals to k vertices. The theorem is true, and we are going to prove that the theorem is true for k plus 1 vertices. So let us go for the corresponding graph is G dash, which is having k plus 1 vertices. So if I am going to remove one vertex from G dash, then the graph is G dash minus V, which is having k number of vertices, and by assumption it is going to be 6 colorable. And any planar graph if I am going to consider, and it is having any vertex if I am going to consider, it is having at most 5 adjacent vertices will be there. Then this we discussed in the previous sessions. And so at most 5 adjacent vertices. So V is also having 5 adjacent vertices. So 5 adjacent vertices will have 5 different colors to make the graph is properly colored. And of course the given vertex is also V. We are going to assign one more color. So it is going to be 6 colors. With the help of 6 colors, V and the remaining adjacent vertices will be properly colored. And of course the remaining is having only k vertices, and it is obviously it is a 6 colorable. From this we can say that it is true for any number of vertices which the graph is having, then it is nothing but a 6 colorable. So with this we are going to conclude this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.